All right. So we are going to basically pick up where we left off last class period. Interesting that I have the back view of you guys this time. Or maybe, I don't know if you have monitors on both sides. I changed the camera, so. All right. Oh, that's what I thought you were like working on a thermostat or something. Oh, well, no. Not a big deal. I can, you don't have your laptop out, so I can't see, the games you're playing, but it's a useful view. Yeah, it's okay. I'm happy looking at the back of your heads. So getting started where we left off, we talked a little bit about psi, what it means, what the importance of it. And so here's some rules regarding psi. Number one is it must be continuous. That is, you can't have a discontinuous jump. Obviously, you can't have a non-function. It can't go like that either. So it's got to be continuous. And except for a very special case, which of course will be the first case we do, the slope must also be continuous. The only situation that allows you to have a non-continuous slope is if you have an infinite boundary. And the very first problem we do in quantum mechanics is a particle in a box which has an infinite boundary. And then the final one is that it must be normalized. You must be able to make it so the sum of all probabilities is 1. So those are 3 really important rules about the wave function. We've already talked about the statistics. That was the primary focus of our class period yesterday, Wednesday, I guess. And so we learned about expectation values. I have a homework assignment for you guys to do since, there's no school on Monday. I assume you guys don't have school on Monday either, right?
Right.
Because it'd be truly a shame if you came to class and I wasn't here. Obviously, I could come in, but so there's a homework assignment with, I'm not sure if it's 3 or 4 problems. It's not posted yet, but it will be posted to Moodle soon. I have it all done, and then I was doing my solutions just to make sure I don't have any problems with the questions. And, well, didn't finish the solutions yet. One thing to keep in mind about the homework is because I gave you a link to a guy's website. He's a former teacher who's worked out every problem in the textbook, doing a nice job explaining how they work. It's a great resource to understand quantum mechanics, but it's kind of silly of me to assign you homework problems from the textbook when you can see great solutions to every problem. So I'm giving you homework problems that they actually just come from another textbook. Yeah, you could probably find that textbook too. But there's at least a much better chance that you will have to sit down and figure it out. I encourage you to work together. Of course, not copying the other person. We don't have person A. There's only 2 of you, so I can't just randomly choose a person. It really sounds accusatory. Person A does the homework, gives it to person B, and he copies it. Make sure that you're both working and that you both develop your understanding. But it's very clear to me that when you get to these problems, you're going to have problems that one person doesn't get and the other person does. And both of you will benefit if the one who understands it explains it to the other person. Because when you're explaining, you start realizing that you maybe were fuzzy on the ideas. You kind of had it, but you understand it better. And then the other person clearly is going to have a better understanding, having explained to them. So I encourage you to do that. I gave you guys my phone number so you can give me a call, send me an email. We can Skype so I can work and show you, whatever it takes for you guys to be able to work the problem successfully. Debbie has a question for you.
So are you seeing Richard's talking at the same time that you hear him, or is it off like it shows for us?
It's on, it's pretty well on, I think.
Yeah.
Okay, good. I just wanted to check. Thank you.
When I waved my hand was back on the table before I saw it move on yours. So that's what she's talking about.
Yeah, our test like this. When we watch ourselves, it's not insane.
I just wanted to make sure because that would not be good to sit there the whole time with it being that way.
They're smart kids, they can deal with it. Okay, so in that homework, you're going to be doing some statistics and then, statistics like we did in class on Wednesday, just with a bigger sample size. And then you're going to be doing problem like I'm going to do just coming up to make sure you have some practice. Now, the position operator in position space is X. Operators. You guys haven't learned yet about operators in your linear algebra class, right? I have no idea where I first learned about operators myself. But operators are functions that act on a function. And they can be as simple as a constant. A times function of X. The A is acting on and doing nothing special. But that's an operator. X is an operator. So I'm going to use, that was perfect. X with a subscript OP. And like I said, I wrote it two ways. I did like that and I did like this. I've seen different books that write the operators different ways. And the X operator is just X. So X operator acting on function of X gives you X times function of X. That looks like a ridiculous equation. But the difference is the left-hand side is saying the operator, the right-hand side is what we call the eigenvalue that you get from that operator. Now the momentum operator, which, yes, I wrote incorrectly the first day of class. It's just a minus sign. I put minus h bar over I, which when I think about it was stupid. The only reason to put over I is so you don't have to put a minus sign, right? Because 1 over I is minus I. This is actually the momentum in the x direction operator is h bar over I d dx. So that's a derivative. The operator is a derivative. So the operators are, they can be sophisticated, but they operate on the function. Because operators operate on functions, as we go through things, the order of where we place things is important because of the operator acting on the things to its right, but not on the things to its left. And we're supposed to, by the end of today's lecture, get through the momentum operator. If not, I have it right here because you have to have it for the homework problem, the last homework problem. Now we're going to do some practice problems. Consider a wave function, and you might remember last class period I used this at the beginning. I didn't have the absolute value sign, I just used the positive. So we want to normalize it and find the expectation values of x and x squared. So going back to our vocabulary, what does it mean to normalize? Not what's the mathematical operation, but what does it mean to normalize?
To set it's whenever you find it by doing it all to 100%, right? So how do you phrase it?
Well, what you said is the essence of what I would say. You're making it so the sum of all probabilities comes up to 1, which is what you were basically saying. It comes to 100%. And then mathematically, that means you're going to integrate because it's continuous over all space. So from minus infinity to plus infinity, because we're given nothing to say that this is bounded. The probability, like that. So that's the actual process for normalizing. Now, in this case, do you see something that's going to make this a little more complicated than what I just wrote?
The mod, right? It's
Well, I'm sorry, I laughed at the wrong time because I thought you were talking about something different. This here looks just like this here, but one's an absolute value sign and one's a mod sign. Right, this here is just absolute value of x. Can you even see where my pointer's going back and forth?
Yeah.
Okay. So that's absolute value, and this is, the mod squared over here. They do fundamentally mean the same thing. But this absolute value sign here is why it's going to be different. Because I need to take from minus infinity to 0, since x is negative, the absolute value of x is going to mean that I'm going to change the sign. And so I'm going to rewrite my psi. And yes, I'm writing it as more lowercase looking, I'm sorry. I'm going to write it like this so we're clear. For x less than 0, And for x greater than 0, so in this case, that absolute value sign means that if I have a negative x, it would be a negative exponent for e here. So this gives me and this one here gives me a negative exponent for x greater than 0. Now, of course, there's also the option of x equals 0. That's a technicality I'm not worried about. Probably should have less than or equal on one of these. What does it matter? One of you is a math major. To that person, it might matter. To me, not so much.
I learned that in physics, not to worry too much.
Okay, good. So I have the function broken out into two regions, so I'm going to do two integrals. One is equal to the integral from minus infinity to 0 of the x less than 0 mod squared psi. So that's going to be a mod squared e to the lambda x e to the minus I omega t e to, actually, I shouldn't go so fast. A star e to the lambda x e to the minus I omega t times a e to the lambda x e to the I omega t dx. So that's the first half going from minus infinity to 0. And then I'll have plus the integral from 0 to infinity of almost the same thing, except for now it's got the minus lambda x So here I've put in the function. And now I'll simplify as I was starting to do last time and realized I probably should be complete and not just simplify right off the bat. In case there is any confusion, which I doubt there is, except for in my writing. This here was psi star, and this here was psi. So simplifying this, a star a is just a mod squared, integral of minus infinity to 0, e to the 2 lambda x dx. Notice e to the minus I omega t times e to the plus I omega t is just 1, as we talked about on Wednesday. And then I have my second integral I have that. If you were even more astute, you could have said, well, this is a symmetric function, and because it's a symmetric function, then I can just do the integral on one side and double it. Right? That's all, so we say, math tricks. So now we have to do this integral. So I'm going to leave it to you. That's I'm going to ask you. I'm not going to just move on. What do I get for the integrals?
E the 2 lambda x over 2 lambda. Is that right?
And what about this one?
You'd have e to the negative 2 lambda x.
Okay, put in our limits and we'll be done. Well, we'll be fundamentally done. I'm going to factor out the a mod squared from everything now. So putting in the upper limit first, that's e to the 0, which is, you know it.
1.
Then the lower limit, what's e to the minus infinity?
0.
Okay. Then we go to the second one, putting in infinity, e to the minus infinity again is 0. And then the final one, so we have 1 over 2 lambda plus 1 over 2 lambda. Oddly enough, then, that's a mod squared over lambda. Remember where we started, this was normalization, so that's equal to 1. Hence, a mod squared is equal to lambda. Now, lambda is a real number, so a mod squared gives us a real number, like it should. What is a?
Square root of lambda.
Now, that is one possible answer. It's the one we always go to. But realistically, you have times any possible theta. Because you could be anywhere on a circle in the complex plane that has a magnitude of square root lambda, and it would still work because we only defined it by the complex conjugate. So usually we just take 0 for that theta and just say it's the square root of lambda, what you said. But just for completeness, you have that option here. So now we've normalized it. Obviously in the homework, you're going to have a different function that you'll be normalizing. Next one, determine the was that a question?
When would e to the I theta, when would that factor in where we wouldn't use 0?
When we start doing things with like eigenvalues and we're using the matrix methods, when I usually do it, you have a magnitude of 1, and you have different ways that you can make the magnitude of 1, and you just randomly choose 1 for this one, then you have to make an orthogonal for the other. And so, they both have magnitude of 1, but they're orthogonal to each other. So that's where I think about it. Okay, next we need to determine the expectation values of x and x squared. So expectation value of x. Now we need to have, what we saw before is going to be slightly different format, but the same meaning. We need the probability times the value, right? And then we integrate over all the possible x's. And so we saw before probability, we saw something like this. And we know that the probability is equal to psi star psi. But the thing is, we need to have the operator operating on psi. And so what we do is we have this is equal to integral of psi star times the x operator times psi dx. So this order is important. You have the complex conjugate of psi, then the operator, then psi, then dx. So to calculate this, I have to have, once again, I have to break it up into two integrals. The x operator acting on psi is x times psi, so this makes it easy. Now, what I didn't do before class was look these integrals up in an integral table. We could integrate them by parts, but do you guys know this offhand, perchance?
You mean by parts or no, this integral?
This integral.
I don't know.
Bummer. Because that's time out of my lecture. Let's see, is it, we don't have an integral table at the beginning of our book, sadly. You will notice on the back of the book, we do have an exponential integral in the back of the book. We have like, what, 10 equations, but one of them is what we need here. If you look down at the 1, 2, 3, 4, 5, 6th, the integral from 0 to infinity of x raised to the n minus x over a is. So we can use that. Changing the limits. I think I have to change them everywhere, right? Well,
Use the integral in the back of the book.
yeah, well, the integral in the back of the book is only 0 to infinity.
You can multiply the other one by 2. Just since it is symmetric.
It's actually anti-symmetric, and so I put a minus sign out front. Right, it's anti-symmetric because we have wait, is it no? Yeah, I got to think about this. Yeah, these two functions are going to be opposite signs of each other because the exponents will be the same sign, but the x's will be the opposite sign. I think I'm right. We'll get, of course, an answer of 0, won't we?
Yeah.
Don't even have to do the math. Oh, wait.
I have indefinite integral of that form. That would help.
Yeah, it's got to be changed like that. But sure, give us the indefinite.
So the indefinite integral would be equal to, I'll give you the form in the back of the book, but it's 1 over a squared times, in parentheses, au minus 1.
AU minus 1?
Yes, a times u minus 1. Times, so the a is inside. It's multiplying the u.
This is working real.
Right?
Yeah, neither of you have your computer, so I can't have you write on. You said, oh, okay, like this. Like that?
Yep.
Yeah.
And then close the parentheses, and then multiply that by e raised to the a times u, where a is your 2 lambda and u is x. Yeah.
Okay. So in that case, then we have well, forget that. So a is 2 lambda. Bueno. Yeah. So putting in 0. And then putting in minus infinity is 0. Hi, everybody. Going to the second term, putting in infinity. And putting in 0. This last one is, there's a -1 here, and it's the second one, so it's minus. That's what's making it positive. And that's completely expected because with a symmetric function about 0, the expectation value is going to be 0.
Nice.
So a lot of work to get a 0. Yay. Then x squared. So now how am I going to do my x squared integral? Actually, let's come way over here. I forgot how far we had traveled abroad. How do we find the expectation value of x squared?
You just do the same thing, except just put the x squared operator in the sandwich.
That's right. Put the x squared operator in the sandwich, as you said. So I'm going to have integral of psi star x operator squared psi dx. Since x operator on psi gives me x, then x operator squared is going to give me x. So I'm doing it in sequence. That's the same as x operator squared on psi. So it comes out to be exactly what you would think, but I showed it in sequence just to make sure. Uh-oh, a little too high. Okay, so now do you have this equivalent formula with x squared in there?
I do, but it comes out to be like a form of integration by parts. If that's okay with you. It's a messy integral.
Yeah, given that we only have 20 minutes left in our class period, I'm going to say you've got to evaluate those integrals at this point. The important part is you instantly saw how to do the expectation value of x squared, which is what is important for this. Doing math is just part of the torture of life. And yeah, you'll have to do it, but if you can see how it's done, we're good with that. For your homework problem, you're going to calculate I'm not sure if I said standard deviation or the variance. Variance is just standard deviation squared. Standard deviation is equal to the square root of the expectation value of x squared minus. So you're going to have to calculate both of those expectation values so you can find the standard deviation.
Okay.
And it tells you to find the expectation value, and then it tells you to find the standard deviation. It doesn't tell you to find, the x squared expectation value, but you have to do it along the way. Okay, now the momentum operator. Find the momentum operator. I just put reference here to page 16 and 17 of the textbook. So go ahead and pull those out. And you see that finding the momentum operator, is a little interesting. And actually, it starts on page 15. Because on page 15, they're saying, well, how do you find the speed? We know how to find the position. How do you find the speed? Well, at your level, everybody knows that speed is the derivative of position with respect to time. So the expectation value for speed should be the derivative of the expectation value for position. And so that's equation 129 in the bottom of page 15. Just saying, we'll just take the derivative of the expectation value. And so it has there the expectation, because the psi or the x operator is just x, that's why it has it written as x and then psi mod squared. And then making substitutions. So for psi mod squared, you can see in equation 129, it's simply been expanded out the derivative with respect, or I take that back. It's been substituted in from what we were looking at yesterday. I got to find where it was now. Equation 1.22 on page 13 was the derivative with respect to time of psi mod squared. So equation 1.22 is substituted in to make equation 1.29 the right-hand side. And notice now we have a derivative with respect to x and then dx. And so then after that, it just goes to how do you solve that integral of x times the derivative with respect to x dx. And it's integration by parts to go from equation 1.29 to equation 1.30. Because you notice it's definitely not the same. The x and the differential have disappeared. And then at that point, you just say, well, the psi star d psi dx and the d psi star x psi, they have the same magnitude. One's positive, one's negative. So you just combine them into one, and you get your final answer for the expectation value of speed then is that 1.31. And so the momentum operator, well, the momentum is just that times mass. And so the momentum operator is going to be derivable from equation 1.33. You have the minus I h bar. What I wrote before at the start of today was h bar over I. Same thing. And then you have this integral psi star d psi dx. Well, if I put an operator between psi star and psi and I get d dx, that must be the operator. So just reading out, I'm going to just write that last part. I know my stars are horrible.
Same.
Well, as long as we have something in common here. I'm just going to rearrange this so it looks the same. Then just by comparison, those have to be the same thing, right? What's different between the two forms in the upper line is that I moved the minus I h bar in between the psi star and the psi. And so there's how you get the momentum operator. We did not go through the derivation carefully because I wanted to make sure I get there. Watch, we'll get to the end of the class period and I'll be like, oh, we got 5 minutes extra. So there's our momentum operator minus I h bar d dx. Which is exactly the same as h bar over I d dx. And you have to wonder just how lazy are physicists that instead of writing a minus sign, we put 1 over I. But it's the same thing, and you'll see it both ways. The answer is we're as lazy as we can be. I mean, that's why we use N for newtons and not kilogram meter per second squared every time. Well, we have some more operators. Kinetic energy. Here's our nifty symbol for kinetic energy that we use sometimes, like in this textbook. And kinetic energy is just 1/2 mv squared, or momentum squared over 2m. So we just take the momentum operator, and you can see here I meant to do Curies, instead I've got these curvy things. So the kinetic energy operator is just going to be the momentum operator squared over 2m. So that's going to be minus I h bar d dx minus I h bar d dx all over 2m. And so you have minus I times minus I is minus 1. H bar times H bar, or H slant times H slant, whatever you call it, squared. And the derivative of a derivative is the second derivative. And so that's our kinetic energy operator. Now we go back to the very first day when I was pointing out the Schrodinger equation. The Schrodinger equation has this acting on psi plus V, the potential energy function acting on psi, is equal to the energy operator acting on psi. So it's simply an energy balance equation. The Schrodinger equation, when you get to that point, suddenly becomes non-mystical. It's just saying the kinetic energy plus the potential energy is equal to the total energy. Now, something about these operators, let's finish this first. Angular momentum, you find the angular momentum operator by taking the cross product of the position operator and the momentum operator. Right now we're working in one dimension, and so we're not going to do that, right? Because you don't have angular momentum in one dimension. But it is going to come up in the future. So just having that out there. I have the uncertainty principle here, but I want to actually go off base a little bit, or off my lecture, and talk about the importance of the operator and, eigenvalue, eigenfunction relationship. So the operators are functions that act on a function and give you a value times the function. So we call that an eigenrelation. If you guys, that you're in linear algebra now, so you probably haven't seen that before, right?
We talked about it a little bit in modern physics, but
okay.
It's not a whole lot.
And then it's come up sometimes in my research, but other than that.
So the basic rule is a operator acting on some wave function psi should give me a value multiplied by psi. Now that a value, we saw with the x operator, it was x, it was a variable actually. So it's not always not a variable, but to have this eigenrelation, you have to have the same function here times the eigenvalue. So using the terminology, this wave function is called the eigenfunction. And then this value here is called the eigenvalue. Anyone here speak German? No? Okay, well, eigen is something on the lines of the one. So it's the value that matches the function. It's forming the system. Not all operators and wave functions work together. For instance, if we take the momentum wave function, we can have, or not the momentum wave function, the momentum operator acting on the wave function, let's say for a free particle. For a free particle, psi is equal to a sine of, and I'm just going to put trying to remember. That'll work. It's something like this. And so x psi is just fine. Right, no problem there. But what if we do the momentum operator? It should come out like that. We should have our eigenvalue, the observable momentum. The eigenvalues are the observables times my original wave function, my eigenfunction. But if you do the math, what do you get? Derivative sine is n pi cosine. So this function, a sine n pi x, which was an eigenfunction of the x operator, is not an eigenfunction of the momentum operator because we don't have our original wave function. So there's some restrictions about wave functions, and the wave function that we're finding with the Schrodinger equation is the one for the energy of the system. So you can actually find other kinds of wave functions from other kinds of equations. They're not the Schrodinger equation anymore. But the Schrodinger equation gives you the wave function with all of our information about the product, the particle. So these eigensystems, we'll be studying them coming up. I just wanted to give a little bit more background on the operator and the eigenfunction relationship so you can see that's actually why we have an uncertainty relation between x and p, between position and momentum, because they don't share the same eigenfunction. If they share the same eigenfunction, you could know them both at the same time. And so then that brings this uncertainty principle stuff. I originally made my lectures using a different textbook, and I was following its organization for the most part. So I think this comes next in our textbook. Actually, no. Next in our textbook is the time-dependent and time-independent Schrodinger equation. So, yeah, this is something that I'll come to, since I have it here. It's easy enough to go out of order from the textbook. The uncertainty principle, as Heisenberg worked out, comes because you don't have the same wave function for both. You can find a momentum space wave function for which you have the momentum operators just p the momentum, and it's very simple. And then the x operator looks very similar to the momentum operator we just worked out. That momentum operator is the momentum operator in position space. And so that's essentially what Heisenberg worked out. He worked out the wave functions. He showed mathematically that if you use a Gaussian distribution, that you will have the best possible combination of smallest uncertainty in position and smallest uncertainty in momentum, right? It's mathematically provable that the Gaussian gives you the minimum possible. And so then he calculated the standard deviation for position, the standard deviation for momentum, and said that the product of those two is always greater than or equal to h bar over 2. And I sure as life hope in the homework I put, that's why I haven't posted the homework yet. Somehow my brain just says, I think I might have used the wrong sign. So I went through either the first or second lecture waving my hands at this, and it's not much better here. De Broglie, using his idea, we have momentum relates to wavelength. Momentum is inversely proportional to the wavelength. So if I take the derivative, d momentum is equal to minus 2 pi h bar over lambda squared d lambda. Is that right? I am doing this on the fly, so it's possible that I'm wrong. So what this tells us is that we have a relationship between wavelength and momentum. And, well, it doesn't follow exactly from what I did there. If we know the wavelength exactly, then our uncertainty in momentum, that is if we know the wavelength exactly, I should have thought this more through before I started. I know my statement is correct, but I know my math is going to be flawed. And that hurts. I don't remember. Yeah, it was last night when I went through this. I don't remember my thought through this, how this equation relates to the statement below. And so I'm going to bring it to this picture. This picture is showing a Gaussian distribution in momentum space. This k is the wave number, which has to do with 1 over wavelength. And so you have an uncertainty in the peak that is, remember when I talked about you have a packet and you say, well, it's somewhere between here and here. We take one standard deviation on either side to say it's going to be somewhere between one standard deviation on either side. And so if we take a Gaussian distribution in momentum space, we have an uncertainty in the wavelength and thus an uncertainty in the momentum. And if we do it in position space, doing the same thing, we have an uncertainty in position. And it's through looking at these two equations or these two relationships and how you transform from momentum space into position space that Heisenberg was able to show his uncertainty relation, which here definitely has the right sign here of greater than or equal to. And I'll fix it before I post the homework to make sure it's right there. This is not the only uncertainty relation. There are other variables that have the same type of relationship. And later on in class, we will learn how to derive the uncertainty relation. So we'll go through this in detail and see how we can find uncertainty relations with various different values. We have to learn what the commutator is first. Okay, we are out of time, and that is the last slide. I am really sorry that I couldn't remember what my math was going from here to there. It seemed clear last night. Before we go, do you have any questions? No. Okay, so I will have the homework posted within a half hour so you can work on it over the weekend. You know, no school Monday. I know we want to honor Martin Luther King Jr., but, you know, it's also time when you work on the homework. And, you know, give me a call or send me an email, whatever, to try to get a hold of me if you have questions.
Okay. All right. Cool. Thank you.
All right. Have a happy Sabbath.
You too.
All right.